Welcome back. This lesson focuses on abstract data types as part of the Python Advanced series of lessons, and it will be covering stacks, queues, linked lists, and binary trees, and their implementation using Python. Again, this is going to be one of those long lessons because we're covering a huge amount of content in it. So do take it slow, take regular breaks, maybe just do stacks first. Then once you're happy with stacks, move on to queues, and then linked lists, and then binary trees. Don't try to tackle the whole lesson at once because it's going to be too much. Hopefully you understood object-oriented programming because we're going to be using some of those concepts in here as well, along with the use of both 1D and 2D arrays. So if you're not familiar with these, what I would probably suggest is go back and watch those videos first so you have a deeper understanding of how to use arrays and classes, and then continue with this particular one. Okay, let's begin. What is an abstract data type? An abstract data type, in simple terms, is just a collection of data and a set of operations that can be performed on that data. Now, most basic or user-defined data types hold data only. For example, name is equal to data. An abstract data type, on the other hand, will have some functions that could apply to that particular data. For example, push the name into a stack, or pop, which basically means remove the data from the stack. Now there are four main types of abstract data types that we need to code, and these are stack, queue, linked list, and binary tree. Now you might even compare an abstract data type to a class where you have a set of attributes and a set of methods that can apply to those attributes. That's why object-oriented programming lends itself really easy to abstract data types. Now remember, a built-in data type is basically string, integers, they are parts of your programming language. User-defined data types are data types that you create, for example, record, pointers, and so on. Whereas an abstract data type is something that you create, which not only just holds data, but also has a set of operations that you can perform on it. Okay, let's begin by looking at what a stack is. A stack basically is a list or an array containing several items operating on the last in, first out principle. So the last item that's pushed into an array is the first one to be removed, which is called pop. So there are two operations: push an item into an array, add it to an array, and then remove an item from an array. But you've got to keep track of the index locations to make sure you know which one was the last one so you can remove it, or where the last one was inserted so you can add to it. A stack can be implemented by using the concepts of arrays and a stack pointer, which basically is a variable. So in Python, all you need to do is simply say names is equal to square brackets, in this case times 5, so it's got 5 items, that's all it needs to have. And a stack pointer, which is going to be set as 0 because index location 0 is the starting point. Now every time I add to this array, I can increment the stack pointer by 1, and every time I pop or remove something from the array, I can just decrease the stack pointer by 1. I don't need to physically remove values from the array. I just need to play around with the pointer, and when I want to add a new value, it'll just override the previous one if there is one in the array. So how does the push operation work? Well, this one pushes a value into the stack and increments the stack pointer. That's all it is. It should also check if the stack pointer is at the 5th position or the last position, because that means that the stack is full. If you don't do that, you're going to get an error and your program will crash. Anyway, let's look at the code. So we're going to define our array names, which is going to have a string in there 5 times because it's just going to be initialized to an empty string. Stack pointer is going to be set at 0. We've got our function push. We're going to push a value in, which is in the brackets as a parameter. Stack pointer is global because we need to access stack pointer inside the function. If I don't do global stack pointer, then I need to define the stack pointer inside the function itself. So the keyword global means that you can refer to variables which are not part of the function. Now, if the stack pointer is greater than 4, which means it's 5, then we print stack is full. Else, we just add the value to the index location identified by the stack pointer. So names bracket stack pointer is the value, and then we increment the stack pointer by 1. That's all there is to a push function. Now let's look at the pop operation. Pop removes a value from the stack and it now decreases or decrements the stack pointer. It should also check if the stack pointer is at the first position because that means that the stack is empty. If you don't do that, then it'll continuously try to remove items which don't actually exist, leading to an error. So we define the function pop. In this case, we don't actually need a value because we're just removing something. Of course, we need the stack pointer, so it's global stack pointer. If stack pointer equals 0, which means it's at the beginning of the array, print the stack is empty. Else, stack pointer is decremented, which is stack pointer minus 1, and then you can do whatever else you need to do. For example, you can print a value out or whatever. In this case, we're just simply printing out the new stack pointer value because that's now going to be the last value in the stack, just for a check. Time for practice question 1. A program needs to use a stack data structure. The stack can store up to 10 integer elements. A 1D array stack data is used to store the stack globally. The global variable stack pointer points to the next available space in the stack and is initialized to 0. Write program code to declare the array and pointer as global data structures, initialize the pointer to 0. So again, pretty straightforward. Pause the video, have a go. If you're not sure, rewind the video and just have a look at what we've done and then continue. You should have something like this, a couple of comments which are declaring stack data as an array of integer, stack pointer as integer. Then you've got global stack data and global stack pointer. The keyword global is essential. If it's mentioned in the exam question, you've got to write it down. And then the stack data is basically an array, in this case 10 zeros, and stack pointer is initialized to 0. That's all there is to this one. This would probably give you 3 to 4 easy marks. Practice question 2. Write a procedure to output all 10 elements in the stack and the value of the stack pointer. A basic loop is all that's needed here. Pause the video and have a go. Just remember the keyword procedure. So this is basically a function that you're going to write in Python. Okay, you should have something like this. Print array function. You got your global stack pointer, your global stack data. For index in range 10, print stack data index. And finally, outside the loop, you're just going to print stack pointer. The idea at the moment is it'll give you a list of zeros, and then the stack pointer is still going to be 0 because we haven't added any values to it yet. Of course, once you add the values, then this will be updated. Practice question 3. The function push takes an integer parameter and returns false if the stack is full. If the stack is not full, it puts the parameter value on the stack, updates the relevant pointer, and returns true. Write program code for the function push. So again, this should be pretty straightforward. Pause the video, have a go, and then continue. You should have something like this. You've defined push, and in the brackets you've got the parameter number, global stack data, global stack pointer as well, because we're referring to the array and the pointer from the start. If stack pointer is greater than 9, basically it's 10, then we have to return false because the array is full, or the stack is full. Else stack data, bracket stack pointer equals number. Stack pointer is incremented by 1, and we return true as the program asks us to do. Hopefully you got this right. If not, pause the video, code this, and then continue. Practice question 4. Edit the main program to test the push function. The main program needs to allow the user to enter 11 numbers and attempt to add these to the stack. Output an appropriate message when a number is added to the stack. Output an appropriate message when a number is not added to the stack if it is full. Output the contents of the stack after attempting to add all 11 numbers. So here we're probably going to do a loop, and we're going to take an input, we're going to get a return back, and based on the return we're either going to say the stack is full or a number was added. Pause the video, have a go at this. It is not a procedure, it is part of the main program, so you just need to make sure you code it that way. Hopefully you got something like this. For index in range 11, in this case, because we need to get 11 inputs, even though our stack can only hold 10 values. Number is equal to integer input. Please enter a number. That's an appropriate prompt. Make sure you always have one. If push number, that's us calling our function, is equals to true, because if the return is true, then we say print number is added to the stack, else print stack is full, because otherwise it's going to be false. And at the end, outside the loop, we're just going to call the print array function, which is just going to print everything out. Hopefully you got something like this. If not, pause the video and then code it yourself and then continue. Practice question 5. You've now got to test your program from the last part, and then you're going to put the following inputs. So run your code, add the following values 11, 12, all the way to 21, and then see what it does. Hopefully you got something like this. You enter the values, and then you get stack is full when you enter 21, and then it prints the values, and at the very end you got the stack pointer. If you haven't got this particular output, then just check your code and then rerun it. Time for practice question 6. The function pop returns -1 if the stack is empty. If the stack is not empty, it returns the element at the top of the stack and updates the relevant pointer. Write program code for the function pop. So we're just basically going to do the removal function. That's pretty straightforward. Pause the video, have a go, and then continue. Hopefully you got something like this. You define the pop function. You got the global stack data, global stack pointer as normal. If the stack pointer is less than 0, that means you return -1. Else stack pointer is decremented. Now, stack pointer minus equals 1 is a quicker way in Python of saying stack pointer is equal to stack pointer minus 1. If you wanted to have this quick method or shorthand, you could also do stack pointer plus equals 1 if you want to add something. And finally, you return the new value that is at the decremented stack pointer by simply saying stack data bracket stack pointer. And that goes back to the main program. If you haven't got something like this, or you couldn't understand it, code this and then continue. And that's about it for stacks. Now, you just tackled an entire exam question based on stacks through the practice questions, and that's all there is to it. This would probably be worth about 25 marks in an exam, an entire question, and hopefully you've understood it. Okay, let's move on to queues. Queues are just like stacks. They're basically a list containing several items operating on a first in, first out principle. So basically here, the first item that's added is the first item to be removed from the queue. So in a queue, there are 2 pointers. Because data is added from the back, we use an end pointer, and because it's removed from the front, we use a start pointer. So the difference between a stack and a queue is the stack only uses 1 pointer, whereas a queue uses 2 pointers, start and end pointers. And it also has 2 operations. Enqueue, this is the operation to add an item to the queue, and dequeue, which is the operation to remove an item from a queue. So one acts like push, the other acts like pop, but they have their own specific names, enqueue and dequeue. So the pronunciation is enqueue in British English. Okay, we're going to look at linear enqueue. So setting up is not a problem. Pause the video and have a look at the code on the right hand side of the screen. It's a list, so we just set up the names array, 10 items. We have a head pointer and a tail pointer. You can call it start pointer, end pointer, doesn't matter. At the beginning, the start pointer is -1 because we haven't added anything to the queue, and the tail pointer is 0 because 0 is the first position of that array. So that's how we set it up. And then we will define our enqueue function, and we have to add some data in. That's going to be in the brackets. And we're going to take names, head pointer and tail pointer as global variables. So that's going to be imported into the function. And then we're going to have a condition which is going to check if the queue is empty. So if the tail pointer is less than 10, which is the max index value, then we insert the item using the tail pointer. So names bracket tail pointer is going to be the data value, and tail pointer is going to be incremented by 1. If the head pointer is going to be equal to -1, then we have to reset the head pointer to 0 because that becomes the start of the list. Else, we just print the queue is full, because if the tail pointer is equal to 10 or greater than 10, quite clearly the queue is full. Now, there are multiple ways to implement queues. This is one of the simplest ones. There are no practice questions for this particular one because we're going to take you step by step through these. So for this one, I would say pause the video and code this yourself to get a better understanding of how queues are developed. Okay, now we're going to look at linear dequeue. And this basically is removing an item from the queue. Again, have a look at the code on the right hand side of the screen. That's where our function is. There are 2 ways that the queue is considered to be empty. And the first way is if the head pointer is pointing towards -1. This will only happen when there is no value enqueued in the queue. Second, if the head pointer is equal to the tail pointer, which means all the values which were enqueued in the queue are now removed. That could happen as well as we continue to add things into the queue. So how does it work? Well, we've got our 3 globals that are imported into this function. We then check if the head pointer is equal to -1. This means the queue is empty. We print that out because we can't remove something if the queue is empty. Else, item is going to be names head pointer. That's going to be the one that we're going to put into this item variable. And then we're going to increment the head pointer by 1 because remember, we're removing this item, and the head pointer will then move to the next index position. So if it was a 0, it becomes 1. So that means the start of the queue is now in position 1, not position 0. So we effectively have removed one item. If head pointer eventually reaches the tail pointer, we can say that all the values are removed or the queue is empty, or we can reset the pointers to create something called a circular queue. And that's something we're going to look at next. What could happen in a linear queue is that you can reach the end and that's it, and you're stuck, you can't do anything. That basically means the only function you can do is the dequeue function, but you won't be able to enqueue anything. So according to the condition of a queue being full, if you wanted to enqueue a new value in, because remember, the head pointer is moving downwards, so the spaces at the top are actually free in a queue. So technically you need to move your tail pointer to the beginning, so everything chases itself. As the tail pointer reaches the maximum value and the head pointer is coming towards it, we can reset that to the beginning, and then when the head pointer reaches the last place, we reset it to the beginning, and that's all it is, and we keep on creating a circular abstract motion. Now have a look at this exam question on a circular queue. A program uses a circular queue to store strings. The queue is created as a 1D array called queue array with 10 string items. The following data is stored about the queue. The head pointer is initialized to 0, tail pointer to 0, number of items in the queue is initialized to 0. Declare the array, head pointer, tail pointer, and the number of items, and if you're writing in Python, include attribute declarations using comments. This is pretty straightforward. It's the first part before the functions, so you should be able to do this. Pause the video, have a go. It's not a practice question. If you're not sure, check the solution next. Okay, so hopefully you got your comment statements where you declared the array as a string type and you got the head pointer, tail pointer, number of items as integer. You then basically initialize the queue array as a string of 10 values. Number of items, head pointer and tail pointer are all initialized to 0. And this would probably be worth about 3 marks. Next, you've got a bit of pseudocode given to you. The function enqueue is written in pseudocode. The function adds data to add to the queue. It returns false if the queue is full and returns true if the item is added. The function is incomplete. There are 5 incomplete statements. Write the program code for the function enqueue. So A, you would have to complete the pseudocode and then code it. So take your time and study the functions enqueue. And you can see that there is something called by ref and by val, by reference and by value. If you're not sure, watch the video on it. However, lucky for you, Python doesn't deal with by reference, so we don't really need to implement that. All we need to do is write a comment statement and we can take care of it. I'm not going to go to the pseudocode itself because I'm going to focus on the code. Hopefully you can use the code to complete the pseudocode and it'll all make sense once I explain it. So look at the code on the right hand side. We start off by writing a little comment statement. If we ever encounter by ref, we simply say that we cannot pass variables by reference, so we declare them as global variables. That's why we use them. So I've got a function enqueue. It takes some input data, and then the rest of the values which are in the function header are your globals. So the queue array is there, the head pointer is there, the tail pointer is there, and the number of items is there as well. If the number of items is greater than or equal to 10, now you can write that equal to 10 because that's the max index. We simply return false because the queue is quite clearly full. Remember, we're implementing a circular queue here, so there is no way for you to check where the end is. In a linear queue, you could go to the end, and if your tail pointer reaches 9, brilliant, you're at the end. You can't add any more because the queue just finishes. But in a circular queue, it resets, so therefore there's no way for you to know if the queue is full. The only way you can know the queue is full if the number of items is incremented to 10. So in this case, if the number of items is equal to 10, return false. We don't really need the greater than sign because that's not in the pseudocode, but force of habit there, so please ignore it. Queue array is going to be tail pointer equals input data. Now obviously we're simply going to add the data at the tail pointer, and if the tail pointer is greater than or equal to 9, then we reset the tail pointer to 0, else tail pointer is incremented by 1, and of course the number of items is also incremented by 1 once we add it. And at the end we return true because we just added an item. So that's all you need to do. The rest is a bit of selection logic. So take your time with this, study the code, write things down to enhance your understanding, or perhaps even try coding it and then continue. Okay, next up is the dequeue function, which returns false if the queue is empty, or it returns the next data item in the queue. Write program code for the function dequeue. So pause the video and have a look at the code. You should probably be picking up a pattern here. We can't pass anything by reference, so we're going to use global variables and arrays, and in our function we've got the globals. We then say that if the number of items equals 0, then we return false because the queue is empty. Else we increment the head pointer. The value array contains the item at the new updated head pointer, and if the head pointer is greater than 9, then the head pointer is reset to 0. The number of items is decremented by 1 because we've just removed something. At the end, we return the value back to the main program. So pause the video and code this if you don't understand how this works. Okay, that's all there is to queues. Let's move on to linked lists. Now hopefully you're taking breaks after each section because this is a long video. Linked list is a data structure used to store a collection of items where each item is linked to the next one using pointers. There are two types of linked lists, ordered and unordered. An ordered linked list is a list where the elements are arranged in ascending or descending order. An unordered linked list is a list where elements are not sorted in any particular order. So you've got to keep an eye on the words used in the exam. If there is an ordered linked list, there is going to be some type of sorting required. If it's an unordered linked list, it's pretty easy. Now you can implement a linked list using two 1D arrays, one for the values and one for the pointers. We use the same index number to represent the data and the relevant pointer, and we also need a start pointer variable. So the setup is like this. You've got a 1D array for pointers where you store 203 minus 1, and you've got 1D array for data where you've got BACD, and then you've got the array index, and the start pointer is 1. So we're starting with index position 1. So we go and we see A. Now A is pointing to index 0, which is in the pointers array. So you go to 0 index, and that is B. So B's pointer is pointing to index 2, so we go to index 2, that is C. C's relevant pointer is pointing to 3, so we go to index 3, which is D. So you end up with A, B, C, D, which is a sorted linked list. Now the pointer in D is -1, and this is called a null pointer, which indicates the end of the linked list. So you can see how we can easily implement linked list using basically two arrays and a pointer. Now, of course, we can also use a class to define a linked list because we can create these nodes, and the node, because there are two values, can have a data and a pointer, which is your next node pointer. We're going to tackle an exam question, and we're going to use a class to create a linked list. So you could see the difference between an array type linked list and a class-based linked list. So here is an unordered linked list which uses a 1D array to store the data. Each item in the linked list is of a record type node with a field data and a field next node. The current contents of the linked list are start pointer, which is set to 0, and an empty list, which is set to 5. Now the index values are listed, the data values are listed, and the next node values are listed. In Python, we can use a class to define a linked list node. And how do we do that? We're just going to start looking at it now. Part A of the question states, the following is in pseudocode for a record type node. Type node, declare data integer, declare next node integer, end type. Write program code to declare the record type node. Now, there is no particular record type node in Python, so we use a class. So here we're simply going to use a class, which is called the node class. And in there, we're going to write in comments public data integer, public next node integer, basically your two variables. And then we're going to have our constructor, which is going to take the data and the next node values, and self.data is going to be that data value, and self.nextNode is going to be that next node value. The P obviously indicates parent, because node is the parent class of everything else that's going to come in. So now using a 1D array and a class combo, we've got to implement the linked list. So how do we do this? Well, part B of the question states, write program code for the main program, declare a 1D array of type node with the identifier linked list, and initialize it with the data shown in the table on page 2. Declare the pointers. Now, I put the data right next to it so you can see this. The code is pretty straightforward. We're creating a linked list, which is an array of 10 items because there are 10 items in here. The data type of that array is the node data type that we've just created, or the node class that we've just created. I'm kind of doing some kind of containment here. Linked list is now going to be equals brackets, that's your array, node 1, 1, node 5, 4, node 6, 7. So you can see that the node class is called 10 times, and the data values for each row are being inserted into the array. So in index position 0, you have node 1, 1. 1 is the data, and 1 is also the next node value. In index position 1, 5 is the data, and 4 is the next node value. So this way we can get all 10 values into the linked list array. Then we initialize start pointer to 0 and empty list to 5. Those were the other two values that were on the previous page that we had to put in. Let's look at unordered linked list insertion. How do you add something to a linked list? The function add node takes the linked list and pointers as parameters, then takes as input the data that needs to be added to the end of the linked list. The function adds the node in the next available space, updates the pointers, and returns true. If there are no empty nodes, it returns false. Write the program code for the function addNode. If you are working with how the pointers are updated, this should be pretty straightforward. AddNode is going to be our function. The current pointer is going to be something that is going to be put in to this function because we want to add node at a particular pointer. So global linked list, global empty list, these are going to be imported. Data is going to be entered by the user. Check if the array is full. That's going to be the first bit. So if the empty list is less than 0 or empty list is greater than 9, we return false because that means there is no available space. Else, add the values to the linked list. So free list is going to be a variable that we've just created, which is going to store the value of the empty list. And empty list is going to now contain the value that is the next node value of whatever was in the empty list. And you're like, okay, why? Because we're updating the pointers, so we need to know where this goes. We then create a new node, which is going to be node, whatever data value the user has entered, and -1. Because why -1? Because this is going to be the last value. The last value always points to -1. And then we insert it in the free list pointer, which is now going to be equal to new node. We're then going to create a variable called previous pointer and initialize it to 0 because we still got to update the pointers to make sure that the new node is linked to a previous node. So while current pointer was not equal to -1, that means it wasn't null, the previous pointer becomes the current pointer, and the current pointer becomes the linked list current pointer's next node value. Now finally, once we've assigned that, and we keep doing this because we want to check all the pointers from the beginning. So we're starting with the current pointer, and then we keep looping it until it reaches the end, which is -1. Once that happens, once that loop is complete and the pointers have been updated, linked list previous pointers next node becomes the free list. So that points to 4. And then we return true that everything's added and the pointers have been updated. Now, if you're not sure, and again, this is going to be very tricky, this is one of the trickiest parts, dealing with pointers, because you have to abstractly imagine how the values are being changed. The best way I've learned how to do this is to trace things out. So run a trace table, practice it. If you don't get it, don't worry, you're not the only one. A lot of students won't get how the pointers are automatically updated, but you will need to trace them out. So create a basic array, or maybe use this one, and then follow the code. Manually write the code, because once you understand what is happening here, you're never going to forget it. So don't continue unless you truly understand how insertion works. Of course, if you do have any questions, please do write them in the comments. However, this will require a lot of practice, or you can just simply say, well, okay, this is what I need to do, memorize the code, and then try to recreate it in the exam. That would work as well. Okay, onwards to deletion now. So how do you delete a particular node? So here we've got to write a function, and we've got to delete items. Now I'm going to put the values here because it'll probably make sense to see the values. Otherwise, the thing with abstract data types are that they are abstract, don't exist in real life, so you have to imagine the possibilities. So we're going to create a function called delete node. We're going to import the linked list, empty list, start pointer. The current pointer is going to be set to the start pointer, which is going to be 0. The data is going to be input, whatever the user wants to be deleted. The previous pointer is going to be initialized to 0. And while the current pointer is not -1, that means that you're not at the end of the list, it's not null, and the linked list current pointer dot data is not equal to the data, then you do this. So previous pointer is equal to current pointer. So previous pointer is going to become the current pointer. And remember, the current pointer is the start pointer, so the previous pointer becomes 0. The current pointer now becomes the linked list current pointer. Remember, current pointer is 0 dot next node. So if you look at index position 0, the next node is 1. So the current pointer becomes 1. So the current pointer is not -1, and we check if the data equals the data in that node. No, it doesn't match. Say we want to delete 6, for example. It doesn't match, then we're going to loop again. Current pointer is not -1. The data is not equal to data at index position 1. which is now 5. We check previous pointer becomes current pointer. So previous pointer becomes 1 because the current pointer is 1. Current pointer becomes linked list 1 dot next node. So linked list index 1, next node is 4. So the current pointer becomes 4. Okay, loop again. Current pointer, is that minus 1? No, it's not, it's 4. And linked list 4, no, that's 2, so that's not true. So we loop again. Previous pointer becomes current pointer is 4, so previous pointer is now 4. Current pointer becomes next node of 4, which is 2. Loop again. Is current pointer minus 1? No, it's not. Is linked list 2 data equals 6? Well, it is. Not equal to 6? Well, quite clearly it is. So we found 6, and then we exit this loop. Now, if current pointer is equal to minus 1, then we return false. That's pretty straightforward. Else, we're now going to update the pointers to remove the node. If current pointer is equal to start pointer, then we just simply update the start pointer to the next node value. That's easy. Else, we're going to go into linked list previous pointer. Previous pointer was already set to 4. We look at the next node and we update it to the current pointer's next node. So we change the values there. Linked list 2.data becomes 0 because we are deleting 6. Linked list 2, which is the current pointer's next node, becomes empty list. Empty list is 5. So from there, go to 5. Empty list becomes the current pointer. So now the next empty list space is going to be position 2 instead of position 5. And then we return true. So the logic works, but you've got to trace it out. And the reason I put this here was because if you were having confusion with insertion, then you need to do a similar exercise so you can trace things out for your understanding. Okay, so how do we go about printing a linked list? The procedure output nodes takes the array and start pointer as parameters. The procedure outputs the data from the linked list by following the next node values. Write program code for the procedure output nodes. So here we're going to create our function output nodes. It's going to have the global linked list. The current pointer is going to be set to the start pointer. While the current pointer is not equal to minus 1, that means it's not empty. Print the string version of the linked list current pointer.data, and the current pointer becomes the linked list current pointer dot next node. All you're simply doing is looking at the first value, outputting it in string format, and then looking at the next node and making that the current pointer, and then looping. And you continue doing that until you reach minus 1. And from the main program, you're going to call the function output nodes, which is going to print out all the values based on the next node in the linked list until it reaches minus 1. So how do we go about searching a linked list? For searching a particular element or value, you're supposed to use the concept of increments in a linked list and compare the value of each element in the linked list with the value you're searching for. And this is basically a linear search. You then return the current pointer as it will be used to increment to the next position. So we're going to create a function called findItem. We're going to import current pointer and search value, whatever we're looking for. While the current pointer is not equal to minus 1, remember the current pointer can be reset to start pointer at the beginning. And if it is not minus 1, then you look at linked list current pointer.data. If it's not matching the search value, then we update the current pointer to the next node. Otherwise, we return current pointer because that means that you found the value. Outside of the loop, we reset the current pointer to minus 1 and return current pointer. That basically means that we haven't found the value and we reach the end of the list. So how do we go about inserting an item in an ordered linked list? It's more or less the same as an unordered linked list, but in this, you first have to find the correct position and then insert the node at the right place. Now this uses a combination of everything you've learned so far. So study the code on the right and see if it actually makes sense to you. So we've got our ordered insertion, we've got the current pointer, just like the unordered version. We've got our globals, we've imported them in, we've got the data inserted. If empty list is less than 0 or greater than 9, then we return false because it's empty. Else, free list becomes empty list becomes the next node at the current empty list. New node is then created, linked list, free list becomes new node. So we add the value in. But how do we update the next nodes? The loop comes into play if current pointer is not equal to minus 1 and linked list current pointer.data is less than the data to insert, because we're now going to keep checking. And this is where your sorting elements comes into play. We update the previous pointer to the current pointer. current pointer becomes the next node. If current pointer is the start pointer, then we change the free list next node to the start pointer, update the start pointer. Otherwise, we update the next node based on the free list to the previous pointer's next node, and so on. And at the end, we return true. Now, again, I'm not going to trace this for you. The best way would be to code this and see the results, trace it out. The logic makes sense, but without tracing this, it will not actually make much sense to you. If you're just sitting there trying to work out what a loop does by just listening to me or reading the code, it becomes very tricky. You've got to have placeholder values, you've got to trace them out. So get a piece of paper, get the original data in, and see how this works. Okay, practice question 7. Time for you to code a linked list. Recreate the linked list in Python itself. So I don't want you to create anything new. I want you to just code the linked list. So just have a go and see if you can output a linked list at the end of it. Okay, hopefully you've had a bit of a break, because linked list should take you at least a week to get to grips with, unless you understood it pretty easily on the first go. We're now going to move on to the last abstract data type, which is the most complex or the most easiest of all, which is called a binary tree. Now, binary tree is a type of data structure in which each node has two children referred to as the left child and the right child. The nodes are arranged in a hierarchical structure with a root node at the top and the leaves at the bottom. Each node will have two pointers, a left pointer and a right pointer, so classes can be used to implement a binary tree just like a linked list. So we will create a class called node, and it's going to have a data value and a left pointer and a right pointer. So it's exactly the same as a linked list with an additional variable. So how do you add a value to the binary tree? Always start by comparing the root, and then if the value that you want to insert is bigger than the root, then you move right. If it's smaller than the root, then you move left. So there is going to be an element of a selection here. So a computer games club wants to run a competition. The club needs a system to store the scores achieved in the competition. A selection of score data is as follows. A linked list of nodes will be used to store the data. Each node consists of a data, a left pointer and a right pointer. The linked list will be organized as a binary tree. Complete the binary tree to show how the score data above will be organized. The symbol presents a null pointer. So you start with the root pointer, which points to 99. Then you look at the value 125, which is greater, so that's on the right hand side. And then you got the value 121, which is less than 125, which goes on to the left hand side of 125. The next value is 97, so you compare it with the root. That's less than that, so it's on the left hand side. Okay, so those are done for you. What about the rest? Where does 109 go? So you compare it with the root. Is it greater? It's greater, so it goes to the right. You compare it with 125. Is it greater or less? It's less, so it goes on the left. Then you compare it with 121. Is it greater or less? It's less than 121, so that'll go on to the left of 121. So then you start with 95. Is 95 greater or less than 99? Less, so you go to the left. Is 95 greater or less than 97? It's less, so it's going to go to the left of 97. And similarly, you can do 135 and 149. Null pointers are pointers that you need to place in those nodes which do not lead to a new value. So if we ended up with 95, there is nothing less than 95. So both left and right pointers are going to be null. So you have to physically write those in the boxes to get the marks. Now, why do we use binary trees? Well, because there is a concept of tree traversal, and tree traversal refers to the process of visiting and examining each node in a tree data structure in a specific order. And this makes life so much easier because we use binary trees for navigation, traffic management, all sorts of things. So there are three ways we can traverse this tree. One is in order, where we check the left-hand side first, the root, and the right-hand side. Then pre-order, where the root is checked first. Then we go left and right. And then post-order, where you do left, right first, and then root. In order means the root is in the middle, A plus B. Pre-order means that the operator or the root is at the front, so it's plus AB. And post-order means that the operator is at the end, so AB plus. If you look at the series of values which are on screen, could you get an answer using in order, pre-order, and post-order traversal? So pause the video and have a look at that screenshot in the right hand corner, and then work out the sequence of numbers starting from the root based on each traversal pattern. And when you've got those, continue on to check the answer. So based on in order, you should have had 4, 8, 9, 10, 25, 30, 40, and 50. Based on pre-order, you should have had 10, 9, 8, 4, 30, 25, 40, and 50. And post-order, you should have had 4, 8, 9, 25, 50, 40, 30, and 10. If you manage to work out the traversal patterns and you got the same sequence of numbers, fantastic. If you didn't, rewind back, look at the sequence, and then work out how we arrived to these set of numbers. So how do we code these traversals? Well, it's better to use recursion, which is a technique where a function calls itself until you reach an exit condition, rather than use standard code. I'm going to be using recursion, even though I haven't touched on recursion yet in programming. This would be your first experience of it in some cases. If you want to know more about recursion, there's a video in the sequence later on which talks about it. But for now, recursion is a technique where a function calls itself, and I'll leave it at that. So we're going to set up our array, which is going to be array nodes, and it's a two-dimensional array, so you've got 3 sets of zeros in there, and then it has 20 rows. We've got a root pointer which is set to -1. We've got a free node which says the first node is free, because we haven't entered anything yet. Now that's how we set our array up. So the in-order function will use this array, and then it will probably use the pointer, which is going to be the root pointer, and you're going to use the selection to check if the array root 0, 0 means the left-hand value. Remember, in the middle array where you have 3 zeros, the left-hand one is the left pointer, the middle one is the data, that's index position 1, and the right one, which is index position 2, is the right pointer. If array root 0, so the first value in the array, which has these 3 sets of values, if that is not -1, because if it's -1, that means you're at the root. There is nothing else to the left of it. If that's not -1, then you call the in-order function again using the array, but this time the root becomes the array root 0. So that means the value on the leftmost place becomes the new root. And this is going to keep on happening until you reach the very last place where there is a -1 to the left of the node. Once you reach that place, you're going to print the array root index position 1. So that means the data value is printed out. And then we do the same thing for array root 2 until we reach -1 there. We keep on calling the function again and again and again. So you do left, which is root 0, middle, which is root 1, and then right, which is root 2. So left, root, right, that is in order. Now if this doesn't make sense, because you probably haven't used recursion before, you can trace this out with a few values, you can even code it, and it will work. Now pre-order traversal is basically the same thing. Our array is exactly the same. We create our function, we import the array and the root as parameters, but this time the root comes first. So we're going to print the root out first, which is going to be array root 1, because 1 is the middle 0 of those 3 sets of zeros. Then we're going to check the left-hand pointers. So we're going to do if array root 0 is not equal to -1, keep calling the same function again and again until you reach -1. Array root 0 is the left pointer, and then if array root 2 is not equal to -1, that's the right hand side. So root 2 is called at the end. So root 1, which is the root 0, which is left, and root 2, which is right. So root, left, right, that's pre-order traversal. So the same code, it's a very easy fix. And post-order traversal, once again, repeats the same thing. Here we do left, right, and root, so the order changes once again. So we define our function, get the array, get the root. This time root 0 not equal to -1, keep calling it again until you hit -1. So root 0 means the left hand side is checked first. Then if root 2 not equal to -1, that means we're checking the right hand side pointers. So we keep on doing that until we hit -1. And then finally we print out the root, which is root 1, which is the middle value. This technique uses recursion and simplifies traversal algorithms. And even if you can't work out how recursion works yet, all you need to do is memorize how the left-hand side and the right-hand side and the root works, and then just rejig them in the exam. So if they ask for post-order traversal, left comes first, which is root 0, right comes second, which is root 2, and then the middle, which is root 1. That's all there is to traversal algorithms. Of course, it's no fun just reading about it and listening about it. It's better to code it. So we're going to look at an exam question. On screen, you see an exam question that came up about binary trees. We're going to work our way through this one. Here we're going to use a 2D array for a binary tree. So the question goes, an ordered binary tree stores integer data in ascending numerical order. The data for the binary tree is stored in a 2D array with the following structure. You got your index, you got your left pointer, you got your data, you got your right pointer. Remember, root 0, root 1, root 2. And you got the values in there. Each row in the table represents one node on the tree. The number -1 represents a null pointer. So that's pretty straightforward. The 2D array nodes is declared with a space for 20 nodes. Each node has a left pointer data and a right pointer. The program also initializes the root pointer to -1, which is the null value, and free node to 0. Write the program code to declare array nodes, root pointer, and free node in the main program. Now, if you were paying attention to the top right-hand corner in the previous section, you will know that this is already done for you. There are multiple ways to do this. You could do it array nodes, 2 square brackets, 0, 0, 0 for x in the range 20. That's one way of doing it. The other way is what you see on screen. Array nodes is equal to brackets 0 times 3. So that's 3 zeros for x in the range 20, and then close the brackets. And that works as well. Root pointer needs to be initialized to -1. Free node needs to be initialized to 0. And of course, the thing I'm missing here are the comments. So how do we add a node to this tree? Because all we've done here at the moment is just initialize it with zeros. Well, first you're going to check if there is a space in your binary tree, comparing the value of the free node. If it has reached the max index, then there is no space as you've reached the end of the array. Then you need to check if the root pointer is still pointing towards -1. That means that there is no item in the binary tree. Then that means you can place your value in there, which is the first index. If the root pointer is not a -1, that means there's already a value in the root. You compare your value to the root value, and if it's left, we go to the left index. If it's greater, then we go to the right index, and we keep repeating this. So you will need to use something called a current pointer, which is going to be written as array current pointer dot left pointer, array current pointer dot right pointer. And because we're using a dot notation, you know that we can implement this as a class and use nodes, which means the methods can be utilized to quickly navigate through and add nodes to a binary tree. So how does the code look like? Now on screen, you see our array. You got your left pointer, data, and right pointer. So we're going to create our function add node. We're going to have global array nodes, global root pointer, global free node. The node data is something that the user is going to input. So we're going to have that as an integer input. And if the free node is less than equal to 19, that means that there is space. Otherwise, the tree is full. So the first part simply says free node less than equals to 19, add the node, else print tree is full. You can obviously flip that around. You can say a free node greater than 19, then print tree is full, else do whatever. It doesn't matter. It's up to you, however the order is. So how do we do this? So array nodes, free node, check the left pointer first. Make sure that that is -1. Array nodes free node 1 will be the node data. Array nodes free node 2 will be -1. Because the left and right pointers of the free node will always be -1. So add that to the free space, wherever the free space is. Now we've got a pointer called free node that identifies this in the array. If the root pointer equals -1, then reset the root pointer to 0, because that's the first node. We are at the root. Otherwise, placed is a flag which is false. We're going to use this to drive a while loop in a moment, and the current pointer is the root pointer. So you're at the root. So we're going to go in there. And while not placed, because it's false, so it'll start the loop. If node data, the data that you've just entered, is less than array nodes current pointer 1, 1 is the middle column. And if you check the value there, if it's less than that, then you check whether it has -1 to the left. If there is -1 to the left, then you say placed is equal to true and you add the value there and you update the pointer that way. Else change the current pointer to the pointer in that node. Now if the node data is not less than the array nodes, that means it's greater than, then we do the same thing but with the right hand side. So we check the right hand side, which is current pointer node 2. If that is -1, then we update the pointers accordingly, set place to true. Otherwise, we keep updating the current pointer. And it's going to keep doing this until placed is equal to true. So the loop will continue on. Talking about code, reading code doesn't make any sense you need to be able to trace it out, you need to be able to code it, and you need to be able to see how it works. If you're not willing to do any of that, chances are that this might go over your head. Now, lucky for us, we do not need to delete a node. We only need to add a node or insert a node into the binary tree. So this is all you need to know for paper 4. All the skills are now covered. Will this get you an A star in the exam? Would you be able to get 65 plus in the exam? No, you're not. You will need to practice. You will need to make sure that your skills are up to scratch, and you need to be able to utilize those skills for a totally new exam question, a totally new context. The more you practice, the better it's going to be. That was a very long lesson. We're going to draw that to a close. So hopefully you understand what abstract data types are and how they're different from user-defined data types and built-in data types. You understand how stacks are implemented in Python. You understand how operations like push and pull work. You understand how queues are implemented and the differences between circular and linear queues. You understand operations like Enqueue and Dequeue. You understand the use of pointers in Python, understand linked list implementation using both classes and or arrays, and understand linked list operations like insert, delete, print, and search. And finally, you had a go at binary tree implementation, and you understand the 3 different types of traversals and what the difference between in, post, and pre-order traversal is. And you can use 2D arrays to implement a binary tree and also add values to a binary tree. If you do have any questions, and chances are you're definitely going to have questions, please post them in the comments and I will get back to you, and I'll see you in the next one.